Yeah, I make a very short introduction. Then we firstly have Dr. Valentin Batager from Circular Project. Then we continue with Angeliki Sarani from BioTheRos Project. And lastly, we have Silja Håkonsen. Sorry for my pronunciation. I don't know if I did correctly. From REFOLUTION project. And we will have some time for Q&A. So all of you can make questions to the speakers, but also to Mika, who is the scientific coordinator of CircularFuels project. Yes, I'll stop sharing. We all know, I consider that it's very important to phase out fossil fuels and also in the aviation sector. So that's why we work for these projects. And at the same time, we also need to do other, instead of only working on different technologies, as you do, which is crucial, we also need to raise awareness about how important the decrease in flight demand is. So we need a holistic approach in order sustainable aviation fuels to also keep up with the demand, which should reach a cap at some point. So yeah, I'm looking forward to hear what the speakers have to say about the projects. And Valentina Batager, you can start presenting your project.
Yeah, so I will try to share my screen. So my name is Valentin Batager of Bauhaus Luftfahrt, and I'm at Bauhaus Luftfahrt. I'm coordinating what we call future aviation fuel research, but I'm also the coordinator of this project CircuLAIR. CircuLAIR is also another Horizon Europe project, specifically looking at aviation fuel production from abundant agricultural residues. And you will see, so in the scope of CircuLAIR and CircularFuels, there are a lot of similarities, but one main difference here is that we aim at hydrothermal liquefaction as main conversion technology. So one more slide of introduction. When we look at aviation fuel consumption and put it in relation, we see that at global scale at the moment, aviation fuels are about 8% of the global refinery output. So the global refinery output is still dominated by diesel fuel and gasoline for road transportation, but it's huge. And when you compare aviation fuels here to the total thing, you see that there's still a huge difference, and we are not the only ones that look into renewable fuels. So there is certainly feedstock composition, especially in the middle distillate markets, and there is just a severe limitation for fuels from waste lipids, so oil, fats, greases, HEFA fuels in aviation. And this is why we urgently need additional pathways to fulfill the targets. And these additional pathways could be biofuels from advanced feedstock and synthetic fuels from hydrogen and CO2. And you will see that we mix both things a little bit in our project. So this is the project partners and a rough sketch of the project, what we are doing. So we at Bauhaus Luftfahrt, as said, we are coordinating the project, also doing system analysis, and I'm guiding you a bit through this graph. So we have manure and straw as feedstocks, and then we have hydrothermal liquefaction coupled with wet oxidation, and this is the core, let's say, innovation core part of the project. This is done by Aarhus University and Circular Nordic, a startup in the field, and then we want to upgrade the biocrudes from hydrothermal liquefaction to jet fuel specification. This is the second main target. Here we have Aalborg University, supported by Topsoe Rice and Eni mainly in this work package. And then we look at a holistic utilization, if we can do so, of almost all carbon in the biomass. So we look at the HDL solids, University of Hohenheim, byproduct recovery, Universidad Complutense de Madrid, and then also we try to capture the CO2 for methanol synthesis, and this is a main lever then to boost the carbon efficiency at the end of the day. So what's also important to say about hydrothermal liquefaction, so the core technology that we have here for biomass conversion, that this has a history. So the CIRCULAIR project was derived in large parts from the consortium of the former HyFlex Fuel project. In HyFlex Fuel, continuous HDL conversion was already demonstrated at a TRL level of about 5. And also jet fuel has been produced. So this is a jet fuel sample from HyFlex Fuel, fulfilling the specification also at lab scale. In that case, this was done also in Aarhus University and Aalborg University. And for specific feedstocks like soot sludge, the technology is already, so to say, at a higher technology readiness level for so commercialization takes place. So this is a unit of our project partner CircularFuels Nordic from another project, sludge to fuel, and this unit was just installed by a customer. So for specific business cases, the technology is already moving up the technological maturity level. And what we do in CircuLair is we do now a project that investigates many other things in a holistic way, and then by this prepares the next wave of the commercialization of the technology. Okay, so why do we use manure and straw? This also dates back to a HyFlex Fuel project work that was done by DBFZ back then. We were looking at several feedstocks, and especially when you look at agricultural residues, you see that manure and straw are really the two big feedstock that dominate the picture. So in that case, we really said this is now the target for the new project because simply because of the availability argument. The main objectives here are to develop and demonstrate a cost-effective pathway to biofuel production from abundant feedstock, but also the cost efficiency claim comes mainly with the manure as a feedstock here. Produce a high share of on-specification jet fuel from HDL biocrudes. This is a target for the upgrading work package. So we prepare for near complete biomass utilization. And one main thing is here the coupling with the green hydrogen. And the fourth main objective is to enable negative contribution to the greenhouse gas balance. And here the solids from HDL play a major role. So I will just quickly go one by one through these objectives. So cost-effective path to biofuels from abundant feedstock. So this comes from HDL, which is increasingly perceived as a prime option for wet waste conversion to biofuels. But HDL also has a process water challenge. And what we do here is we address this process water challenge by wet oxidation of the HDL process water. And this does two things. So the COD of the water is reduced, but this is also an exothermal process. And so the hope is that we can have autothermal HDL, meaning that we don't need external heat supply, but at least what we see now is that at least a high share of the process heat demand can be covered by wet oxidation. But it also looks at the moment as if we could kind of achieve this autothermal HDL goal. On the right-hand side, you see a little bit the effect of wet oxidation. So left is a typical process water from HDL conversion. And on the right-hand side, you see the process water after the treatment under specific temperatures and also under specific durations of running the wet oxidation process. So you can play with it and then have different outcomes. High share of on-specification jet fuel from HDL biocrude. So what the project partners are doing there is developing tailored upgrading schemes to convert the biocrude to on-specification jet fuel. And one important thing here is hydrocracking also of the distillation residue. So in principle, it's a strategy where we have some pre-treatment of the biocrude, and we go to fixed bed hydrotreating, have slurry hydrotreating as an alternative here, and then we go towards the jet fuels, but the bottom residue then again will be cracked in order to increase the share of jet fuel that we have at the end. And if you look, and this is prior data from HyFlex Fuel, if you look at the composition of these jet fuels that are made from hydrothermal liquefaction, it's very interesting because they also contain a lot of this cyclic molecules. So what you see as a molecular distribution is pretty similar to what we have for jet fuel at the moment. So this coupling with the green hydrogen world for near complete biomass utilization aims mainly on a recovery of CO2, both from the HDL gas and the wet oxidation gas. Then we convert this CO2 to green methanol using green hydrogen. And the project also contains a small demonstration of methanol production, which aims mainly on the purity level of the CO2, because methanol synthesis itself is a TRL9 process. In addition to this methanol production, we try to recover volatile fatty acids and ammonia from the process water after wet oxidation. And this is one feature of this wet oxidation process, that the carbon species that are initially in the HDL process water are mainly converted to volatile fatty acids with a high share of acetic acid, and we try to recover it. And of course, the soil amendment by the HDL solids. Last target, negative contributions to the greenhouse gas balance of HDL. Here the main target is to do research what we can do with the HDL solids in agriculture. But there's also another thing, and the other thing is more from a system analysis perspective, but gives us likely a larger lever, and this is the change in manure handling practice, because we work with manure as a feedstock here, and avoided emissions from compared to the current manure handling can be a big thing here on the balancing sheet. So further options could relate to the feedstock, and of course one could also think about sequestration of CO2 streams. So summary conclusion. So we will need liquid fuels to achieve the climate targets in aviation and also shipping. And we have a specific need for fuels from advanced biomass feedstock and from wind and solar. Both things are addressed here in the CircuLair project. The prior project, HyFlex Fuel, demonstrated HDL conversion and upgrading of various feedstock, and commercialization is underway for HDL for selected cases, such as soot sludge. In our new project, we do several things. So we aim at HDL conversion of abundant agricultural residues, manure mainly, and straw. We address the process water challenge of HDL by wet oxidation. We try to maximize the jet fuel yield and quality by appropriate upgrading schemes, enable almost complete feedstock utilization by coupling with green hydrogen. And at the end, we try to close the knowledge gap regarding the use of HDL solids for soil amendment and carbon sequestration. So that's it. So thank you for the opportunity to present here. And I believe questions will then be asked after all presentations in a Q&A session, correct?
Yes, that's right.
My name is Angeliki Sagani. I am a research engineer at Center for Research and Technology Hellas. CERT puts a strong emphasis on technological innovation, and within this context, it coordinates the BioTheRos project, which is dedicated to the collaborative actions to bring novel biofuels thermochemical routes into industrial scale, which I'm going to present in more detail today. BioTheRos is a European Horizon program running from 2023, and the project is made up of six consortium members from different European countries, including the Biomass Technology Group, BTG, from the Netherlands, the Best Bioenergy and Sustainable Technologies from Austria, the Circe Technology from Spain, the Motor Oil Hellas, and of course the WIP Renewable Energies. The BioTheRos project will be applied in pyrolysis and upgrading units in Netherlands, in the BTG facilities, and a gasification unit within the best facilities in Austria. The BioTheRos goal is to transfer biomass into an opportunity by developing a comprehensive approach that will accelerate the production of sustainable biofuels. Within this context, synergies between technical, industrial, and research stakeholders are foreseen to maximize the circular economy-based scale-up of maritime and aviation biofuels through innovative thermochemical conventional technologies. In more specific, the BioTheRos has specific targets, including the deployment of cost-effective and sustainable technologies, namely the pyrolysis and upgrade of the intermediate products and the gasification and Fischer-Tropsch synthesis, so as to produce from different biomass feedstock biofuels, aviation and maritime biofuels to TRL-5. An additional objective is the selection and assessment of several biomass feedstock via predictive biomass demand artificial models utilization. At this point, it is very important to note that a European and global analysis of no-food feed biomass resources has been carried out so as to select bio-waste and bioproducts derived from the industry and primary sector. Furthermore, BioTheRos aims to develop scale-up rules of biofuels production via advanced modeling techniques as well as lab and pilot scale trials to develop a holistic sustainability assessment framework based on the life cycle principles so as to integrate technical, environmental, economic, and social parameters via multi-criteria decision analysis techniques to evaluate the efficiency of its BioTheRos value chains. An additional objective is to investigate the market dynamics of the scale-up pyrolysis and gasification biofuel value chains. And finally, the knowledge exchange among the international stakeholders so as to improve the global knowledge on sustainable biofuels. What is the BioTheRos breakthrough? I think that this is the most important question. The main contribution of BioTheRos is to develop novel and cost-competitive fast pyrolysis to biofuels and gasification synthesis value chains, combining carbon capture utilization and fuel upgrading for accelerating the scale-up of sustainable biofuels. The breakthroughs within the BioTheRos project are elaborated by demonstrating the full value chain of both pyrolysis and gasification technologies from biomass collection to high quality jet and marine fuel production, the integration of a novel carbon capture unit of gases from both the fast pyrolysis and the gasification processes, the utilization of renewable hydrogen as an add-in option so as to produce advanced aviation and marine biofuels, the development of a holistic methodological framework in order to highlight the potential opportunities and the handicaps for the scale-up of biofuels, as well as the increased market uptake of advanced biofuels in both aviation and shipping, and finally, the development of a holistic life cycle decision analysis alongside a novel multi-criteria decision analysis methodologies so as to optimize the value chains for the production of biofuels in industrial scale. Now, I will proceed with a brief description of the two demo sites and the related technologies, the pyrolysis unit within the PTG facilities and the gasification later plant within best facilities. Regarding the pyrolysis unit, the PTG operates in its lab a pyrolysis bench scale unit with a mass flow of about 2 to 5 kilos per hour and of course a larger scale or pilot plant with a mass flows up to 200 kilos per hour. For the upgrading of the pyrolysis oil to transport fuel, a continuous upgrading unit will be employed. The whole fast pyrolysis value chains include all the processes from the collection of the biomass feedstock, namely forestry residues and the barley straw, its pre-treatment process and its transportation to the pyrolysis unit so as to produce the fast pyrolysis bio-oil, and of course the upgrade of the fast pyrolysis bio-oil through a multi-step hydrotreatment process so as to produce the sustainable hydrotreated pyrolysis oil. This will be fractionated in the end into naphtha, sustainable aviation fuel, and renewable marine diesel. Regarding the gasification unit in Austria, BEST operates in its plant a 1 megawatt scale gasification reactor with a mass flow of about 200 kilos per hour and a 250 kilowatt pilot Fischer-Tropsch synthesis unit with a produced raw product estimated at about 20 liters. For the upgrading of the Fischer-Tropsch waxes, a hydrocracking pilot plant unit in Greece will be also utilized. In this case, the feedstock for the gasification value chain includes high-quality wood chips as a reference scenario, and as an alternative scenario to be investigated in detail, forestry residues, tree tops, which are of course biogenic. The gasification value chain includes all the processes for the forestry residues collection up to the gasification process for the production of the gas, the coarse gas cleaning and the fine glass cleaning to obtain the hydrogen-rich synthesis gas, up to the sustainable biorefinery products production. Both the technologies will be investigated at lab, pilot and demonstration scale so as to investigate the potential for industrial implementation. The BioTheRos methodology in general will apply a multidisciplinary stepwise approach, including the selection of feedstock through artificial intelligence algorithms, the pilot experimental validation, the scale-up simulation and process modeling, the environmental, techno-economic and social assessment based on life cycle thinking for the sustainable scaling of advanced biofuels value chains, and of course, pyrolysis and gasification technologies, as I mentioned, will form the core value chains for this approach application. In more detail, the methodology is divided into four main steps: the mapping of biomass feedstock and circular bioeconomy options based on technical parameters, the market requirements, as well as considering the compliance with environmental policies, for example, the RED II directive regarding the biofuels, the testing and validation of technologies at both a lab, pilot and demonstration scale, with biofuel evaluation based on aviation and maritime fuel standards, a techno-economic analysis alongside business model developments so as to boost the biofuels market penetration focusing in factoring market dynamics and international scale-up rules. And last but not least, the joint application of life cycle sustainability assessment, considering economic, technical, environmental, and social aspects, alongside a novel HP TOPSIS multi-criteria decision analysis methodologies that is going to be developed by CERF for the performance assessment and selection of the most sustainable biofuel production route from a circular economy perspective. Now, how will BioTheRos contribute to biofuels promotion? This will be achieved by mapping of the biomass potential, which promotes the optimization of biomass to biofuel value chains, the experimental valuation of the BioTheRos thermochemical technologies so as to identify the key handicaps and risks for building global knowledge for upscaling, the overcoming of the technical bottlenecks and integration, of course, of carbon capture utilization and renewable sources, hydrogen, to enhance the efficiency of the advanced biofuel production, the multi-criteria analysis to define the best available scenario so as to enable coordinate actions between the industrial stakeholders and, of course, the end user. The techno-economic analysis to evaluate the economic performance of the biofuel production so as to promote the creation of new market opportunities. And finally, the exchange knowledge between the BioTheRos and international network so as to promote collaboration opportunities and identify the innovation needs. Potential synergies within this BioTheRos project will be carried out among government and regulatory bodies, research stakeholders, fuel producers and suppliers, of course airlines and shipping companies, biomass providers, and finally the general public. And that's all from my side. I think that in the end, I will be more than happy to answer any questions you may have.
Thank you, Angeliki. Yes, I've chosen these projects because they have a similar similar feedstock with the ones that we use at CircularFuels, and also, for instance, with the first project, we also use green hydrogen. So it's very nice to see what all of you are doing. We can continue with the next project with REFOLUTION that Silje Fosse Håkonsen works for. So you can start your presentation.
So good morning, everyone, and thank you for the invitation to present REFOLUTION. My name is Silje Fosse Håkonsen. I'm a research scientist at SINTEF, and we are coordinating the REFOLUTION project, which stands for Refinery Integration, Scale Up and Certification for Aviation and Marine Biofuels Production. So this is a 4-year project. It's an innovation action, and we are well into the 2nd year of the project. We are looking into upgrading and refinery of pyrolysis liquids into refinery technologies and targeting aviation and marine biofuels. I just want to give a bit of a background for why we started discussing REFOLUTION and made this initiative and applied for this project. So it started, say, more than 10 years ago with a project called FastCard that looked into gasification and pyrolysis routes for biofuels production in general. And one of the outcomes from that project was that the pyrolysis routes looked quite promising. So a follow-up project from that was called For Refinery, which looked at 2 liquefaction technologies, so both pyrolysis and HTL. And we looked at different lignocellulosic feedstocks and how these could be co-processed in refinery technologies. So on board on that project, we had refinery partners such as Repsol and MOL. And a bit later, but almost in parallel, we had another project called Waste to Road. It was quite similar project, but looking at different sorts of feedstocks. So mostly municipal wastes, contaminated wood, and those things. But the sort of goal was the same: to use pyrolysis and HTL to liquefy these feedstocks and to co-process these in refineries. So that led to REFOLUTION. So as I mentioned, this is an innovation action, so it's targeting quite higher TRL than the project that we worked on before this. So for the aviation fuels, we are targeting a TRL 7, and for the marine sectors, a TRL 6. I'll try to walk you through this scheme. So we are looking at biomass feedstocks, so forestry residues, and pyrolysis as the liquefaction route. We are not, in this project, we are not looking at the pyrolysis technology per se, as this is quite mature, but we are more looking into how this can be upgraded and refined and co-processed in refineries to get the product that we are targeting. So you could say we have two routes, so to say. One is to go from the pyrolysis biocrude through stabilization and deoxygenation, and then to do a hydrotreatment of this stream, and then to target marine biofuels. Another way, other route we are looking into in the project is to take various degrees of stabilized pyrolysis liquid and do co-refining in a fluidized catalytic cracker. So this is co-refining, so that will be together with a fossil stream. Then to do a separation and to do a hydrotreatment of the kerosene fraction to target aviation fuels. But we are also, from the catalytic cracker, we will have a range of products. So we are also looking into what this co-refining with biocrude, how that will influence the other products from that technology. So that is sort of the core technologies that we are working on. So to optimize the biomass conversion processes, to get improved product yield, and to do this in a cost-effective way. One thing that is important for this project is that if we add a biocrude into the catalytic cracker, the refineries cannot sell any of the products from this as jet fuel. So if the refineries choose to do co-refining with the biomass or biocrude, then we would have to certify, to do a certification process of the aviation fuel. So we will not do a certification in this project, but we are sort of doing a pre-assessment of the fuels and sort of laying a certification process that can be utilized after the project, and also produce quite some volumes of products that can go into a future certification process. We're also looking into process design, increased digitalization, and also tracking of green carbon. Because once you do co-refining and you do a separation of all of your products, to develop a method where we can say, in this product fraction, we have so and so much percentage of green carbon. So this figure really shows much of the same, but in a more clearer scheme, perhaps. As I said, we're not looking at the pyrolysis oil conversion step, but more on the and finding how much of stabilization and refinery do you have to do to get a product that is quite similar to a fossil sort of replacement. And this is also, as I will come more back into, it's a lot of creating smaller samples in the beginning of the project, doing a pre-assessment of the fuels, and sort of having that feedback loop back into the testing, and to have this iteration where we can really optimize on a good product. So for the aviation fuels, as I said, this is co-processing in a fluidized catalytic cracker. We are doing this in the project. We're doing this in 3 different scales. So we have a lab scale downer unit that is, so because a traditional catalytic cracker is a riser, but this is a downer. Which is run by the University of Groningen, but is located at BTG. So the goal or the meaning of that unit is to be able to vary conditions and test different kinds of catalysts to make small samples where we can do a sort of a pre-screening of samples and see what conditions and catalysts that gives us the best product. We also have a pilot scale unit that is sepsis, which has just started running this summer on co-processing. And then in this project, we are configuring a unit that is located at VTT to be able to do catalytic cracking at the demo scale. And we need this unit to be able to produce the amounts that are necessary to do sort of a full assessment of the fuels. In parallel to that, we are working on process design and modeling. We have existing fluidized catalytic cracker models with fossil fuels, and to extend these models with bio-based compounds, and that will be done based on feedstocks, analytical data, and also on the experiments that we run in the units in the project. And once the models is extended with these bio-based compounds, to implement this in a flow sheet, a simulator, and to have a model that we can operate in parallel to operating the actual units. A lot of focus is on this project, both on the aviation and marine, is on fuel validation, standardization, and certification. For the aviation fuels, as I mentioned, it has a lot to do with that this route needs to be certified, but also for the marine section, we need to have some standards that we can work on in the future. So they will be done at 2 different levels, so to say. So a low fidelity assessment, a sort of pre-screening where we have low volumes of the feed or the products. And then later in the project, we will have a high fidelity assessment of potential fuel candidates. Yeah, this is really just saying more of what I just mentioned, but yeah, there are ASTM standards, there are ISO standards that needs to be applied to go through these assessments of the fuels. At the end of the project, the goal is to have done a high fidelity assessment of both the aviation and the marine fuels. And for the marine fuels, we will also do engine tests at the one-cylinder marine engine that is located at the University of Rostock. Another part of the project that we work on is the sustainabilities of these processes. So we have, from quite early in the project, worked on this responsible research and innovation framework and process. So this has been, in the project, doing a lot of workshopping with different project partners to lay out that framework. Currently, we are also planning for a workshop in social acceptance for next year, because we see that as one of the barriers to be able to take this technology further and to really do the implementation of this technology, is that particularly here in Norway, we've seen that it's media sort of doesn't talk well about it, and that influences the public opinion on this. And we've seen this with, for example, land-based windmills, that they've had to stop these projects because of the public opinion. So how can we sort of reach out to the sort of wider public and not just sort of the technologies experts? So there will be a workshop on that next year, and we will of course also reach out to these other projects that are working on similar things. So I will just sum up with this slide. This is the partners in the project. In this project, we have OMV and Neste and Cepsa as the refinery partners. You will see DLR, which is responsible for the fuel assessment for aviation fuel. We have Grace that is providing us with the catalyst. And BTG that is supplying us with the pyrolysis liquids. So I think I will end with that. And of course, you can follow us in social medias or contact us directly. So thank you for your attention.
Thank you, Lucia, for your presentation. I think it's very important that you also focus on the general public's acceptance of sustainable aviation fuels, because, as you said, that it can be a great obstacle. We also have some common partners like CNRS and VCT are also partners of the CircularFuels project. Okay, I think now it's time to move to the Q&A session. So please take the opportunity to make some questions.
Oh, thank you. And thank you everybody for really, really interesting presentations. And I'm happy to see so much similarities with our CircularFuels project. And maybe a common question, or maybe a proposal even to everyone, that for example in our project we are using also fast pyrolysis driven by solar thermal energy, and then upgrading the pyrolysis oil with hydrogen, green hydrogen, done with electrolysis and solar PV. But of course, the first step, as you all showed, is that like understanding the capacity, how much feedstock you have available. I think it would be very nice to maybe have a discussion this afterwards. That what are your results, and maybe we could compare, and because we are definitely planning to make a publication of this. And maybe it would be nice to have another meeting also going to the volumes available and how much from the, for example, SAF we can cover from these feedstocks. So maybe if all the presenters, you could comment that, what do you think about it, and how do you see it at the moment, that how much there's volumes available? What is the fraction for example, in EU we could cover based on these feedstocks? So that's all from me, but thanks you, very, very good presentations.
Maybe we can start with Valentin answering question.
Yeah. So I showed this slide with the feedstock assessment, and this was spatially explicit, done by DBFZ, and this data is published. So in our project at the moment, we are not going to repeat it. So you can look at the data of DBFZ, please contact me and I can make the contact and send you the link. What we do in the project is more like looking how can we aggregate the feedstock in a specific local context. How can we bring this together with green hydrogen in a meaningful way? This is intermittent, the feedstock supply will be different, and so on. So we are looking more into this specific details that then relate not so much to feedstock availability, but to, let's say, the fraction of the feedstock that we can then really meaningfully bring into the system.
Thank you. And of course, yeah, we are also focusing on the technical details, but as a first work package, we map the feedstock availability. But I will get back to you, and we will get back to you and ask about the public data. Thanks a lot, Valentin. Very good.
Maybe Gelki can continue.
Yes. Thank you. This is really a very interesting question. However, BioTheRos, it is still in a preliminary phase on this potential biomass potential and assessment. However, within our task, we are going to carry out an integrated biomass potential assessment for non-food resources. So I think we can have a further discussion in some months since we will have our results as well.
Okay, thank you, Angeliki. Very nice.
Especially, we analyze all what market volume can be covered with the biomass considered. We also compare it with the proposed legislation, and we identify how many new units are necessary for per each country. So I think as the next conversation, we have a lot to discuss about this issue.
Okay, Gelki. Now we can hear Celia.
Yeah, we are not looking into that in the project for the REFOLUTION, but in full refinery, we did work on this, and there we looked at different feedstocks, sort of representative from different parts of Europe. So looked at straw, eucalyptus. We looked at forest residue, which is more common in Northern Europe. Unfortunately, I don't have the numbers available right now, and I'm not sure if they were ever published. So I have to go back and check on that.
Yeah, thanks. That would be great. But just my point is kind of securing the number. There could be a lot of errors in this, and to have as reliable estimate for the potential, that would be very crucial. But thanks, Celia. Very good.
No problem. And another aspect of that, I think, is that this will probably be a resource where we have competitions from in the future. There are a lot of different technologies that are being developed based on biomass.
Exactly.
Yeah.
I fully agree with that.
Yeah.
Okay, but thanks. Stavros, you have also a hand.
Yes, thank you all for the very interesting presentations. I have actually two questions, one for the first speaker and one for the REFOLUTION project. Do you consider in the HCl treatment of the process water of the HCl treatment with water oxidation? Do you consider the capital costs? Because as far as I remember, water oxidation, for instance, for municipal wastewater, was just to be a very expensive process to operate and to build. Is this considered a capital cost assessment of this option?
Yeah, we did not finish the techno-economic analysis yet, but of course this is one of the concerns. So what we get is we get likely HDL that doesn't need much external heat anymore. So this is a plus in terms of techno-economic assessment, but we have additional capex. So and then we need to see how this plays out at the end of the day. One important thing is that wet oxidation operates at very similar conditions as HDL. So like 200 bars pressures, same temperature level, and so on. So this is something that is not easy to implement elsewhere, but here it's exactly the same conditions that we have as for HDL, only a bit easier as we're not working with the slurry but with the process water. So I think still we need to show that this extra capex pays off at the end of the day, especially also for in comparison to other methods to deal with the process water. So anaerobic digestion could be an option or so. But I would not be too much afraid here, because it's exactly the same stuff that we need for HDL, only a bit easier.
Okay, that was my point. That you are indeed you are making a techno-economic analysis, a capital cost estimation, right? It's not only on theoretical coupling of energy flows.
Yeah. Otherwise, you could not win a Horizon Europe project. So, yeah,
No,
of course we will do it. Yeah, but it's exactly what I think, and I think we need to establish these lighthouse cases where we really make commercial availability also for selected things. And what you're pointing out here, if we find out that this let's say additional capex is too painful, then this could of course be a bottleneck for this.
No, but I share your point about synergies because of the operating conditions and because of the heat recovery nearby. My other question that also is important for us for the REFOLUTION project, I saw that in your options, only after co-treating with in a FCC unit, you go for aviation fuels. Why not a continuous hydrocracking of the bio-oil standalone goes to aviation fuels and it goes only to marine fuel? So you are maximizing diesel in the REFOLUTION project, I suspect, right? For the standard process.
Could you repeat that last sentence, please?
So I saw in your slides that you had two options, and only the co-treatment of the stabilized pyrolysis oil leads to an option of aviation fuels.
Yes.
When you are not co-treating, you only go for a marine fuels. I suspect this is something similar to diesel or something like that, right?
Yeah, it depends on the sort of boiling point range where you sort of define your marine fuel, but yeah, it's diesel marine. Yeah.
Has it been shown by your very many previous projects that technologically hydrocracking of the oil up to aviation fuels is not economically feasible? Why don't you go for aviation fuels also with this path without co-treating?
We have discussed, and we have another project that is called Fuel Up, that is sort of assessing more the direct route to aviation fuels, not with co-processing. In this project, we discussed other technologies, but since we wanted to aim at such a high TRL, then we landed on co-processing in the FCC for the aviation fuels. Yes. So no, we are not considering in this project the other route.
Is there any other question? Okay, from Sabrina, yes.
Hello to all. Thank you for your nice presentations and Charity for organizing this nice event. I have a question for Valentin. Thank you for sharing your presentation. I just went through quick your presentation, and I would like to ask you, this database, which is public, is based on historical data, or you have done any forecasting for 2030 and 2050 about the availability of the feedstock?
So back then, this was a state-of-the-art analysis, so not including like the projection. Also because we think that these things could be implemented more in a medium-term time scale, and for us, this spatially explicit evaluations were more like assessing the situation as it is today. I don't know if this level of detail makes any sense to any projection to 2050. Maybe adding something else to the question before with the capital cost. Now, when you think about wet oxidation, usually you need to pressurize air to high pressure. So this also costs a lot of energy. Now, when we can have an electrolyzer or a pressurized electrolyzer that gives us pure oxygen already at elevated pressure, this can also make a difference.
Any other question? Yes, Sylvain, you can go.
Yeah, thank you for all the speakers. I have a question for Valentin. What is the temperature and pressure of the hydrothermal liquefaction?
So the pressure level is 200 bars or slightly above. So hydrothermal liquefaction comes in two versions. So you can be subcritical or supercritical. So we go for subcritical. Still pressures are on the order of 200 bar and slightly above. And then the temperature is an important thing for consideration. So we are operating somewhere between 325 and 350, where 350 likely gives us a better quality of the oil, but then we have a problem with the thermal exchange with the wet oxidation, because we need to go to even higher temperatures. So this is the goal the game we play a little bit at the moment. But something like close to 350 degrees Celsius would give you a nicer quality of the biocrude from feedstocks such as soot sludge or manure.
Okay, so just a remark, it could be a temperature that is easy to supply by thermal solar energy, which is something we are looking at the CircularFuels project, but at much higher temperature. But if we go to this kind of temperature, it's very mature, and so it could be also supplied by external heat from thermal solar power.
Yeah, it's true. But when you look at the presentation that I just shared in the chat, where we have the large problems with the manure, yeah, so really disposal problems with the manure, and this is the areas we are targeting. It's not the nice DNI locations. So, yeah. But of course, you're correct. For soot sludge, HDL in Egypt or so, it could make sense.
Yes, Mika, you can.
Yeah, I guess shortly. We are running over time. Yeah, also, like, just to let you know that we have been also working with supercritical water gasification and HDL, doing mostly modeling, but also experimental work in Åbo Academy. And I think that for sewage sludge, if the water content is high, then it's easy, like pumping is easy. But I think for manure, it might be, depending on what animal is the source, it can be, like the viscosity might be a problem. Like there's like precipitation impacts, and those can be severe. But I think that, Sylvain, your point is very good, that kind of having the liquid on the other side of the tube and solar irradiance on the other side. That would be a very interesting option to study. Yeah, thanks.
Indeed, this sounds interesting. As we're running out of time, I think it's time to wrap up this event. And I'd like to thank all of the speakers, all of the 3 speakers who were willing to present their projects, and all of you who joined the event and for making questions. So thanks a lot, and maybe I hope that this online meeting is the beginning of collaboration between among us, and who knows, maybe we'll meet in person at a conference. Yes. So,
I agree.
Thank you.
Actually, thank you very much for organizing that on behalf of the CircularFuels, and I think it is very, very well organized, and I fully agree that there would be a lot of opportunities for collaboration in the future. So let's hope to see in the future, and these type of events are very useful, I think. So thank you, everybody. Have a nice afternoon on my behalf.
Thank you.
Thank you. Goodbye.
Bye-bye.
Thank you.
Have a nice day.
Thank you. Bye. Have a nice day.
Thank you.
Bye.